Welcome. Today we're going to break down a real GCSE chemistry exam question all about chromatography. We're not just going to find the answers, we're going to dig into the thinking behind them so you know exactly how to lock in every single one of those marks. So here's our plan. We'll start with a classic calculation. Then we'll analyze the chromatogram itself. After that, we'll see how we could improve the experiment, link it all to the real world, and finish up by making sure we nail the core concept of RF values. All right, let's dive right in. The first part is a calculation. This is a super common way these kinds of questions kick off. We've got an RF value, and we need to use it to figure out a distance. Okay, so here's the problem, pulled straight from the exam paper. We've got two bits of info to work with. The RF value for the yellow dye is 0.60, and we know that dye has traveled 5.7 centimeters. The mission? Calculate how far the solvent moved in total. Now, to solve this, there is one thing you absolutely have to know, and that's the formula. The RF value is just a ratio. It's the distance the dye moved divided by the distance the solvent moved. Simple as that, but you gotta have it locked in your memory. The actual working is just a three-step dance. First, you've got to rearrange that formula so you're solving for the distance the solvent moved. Easy enough. Step 2, you plug in the numbers the question gave us. And finally, step 3, you just do the math. And boom, the calculation gives us our answer. 9.5. Don't forget the units, in this case, centimeters. That's a nice, clean 3 marks in the bag. Okay, on to part 2. We're shifting gears now from calculation to analysis. The question wants us to look closer at that chromatography and think about what we can't see. Now, this is a fantastic question because it forces you to think about the limitations of this whole technique. We're told the ink has more than 2 things in it. So, where are the others? Why do we only see 2 spots? So, the official mark scheme actually gives 2 possible correct answers here, and you just need one of them. The first idea is pretty straightforward. Maybe some of the compounds in the ink are just colorless. They've separated out, but we can't see them. The second idea is a bit more subtle. What if another compound has the exact same RF value as one of the spots we do see? It would have traveled the same distance and be hiding right on top of it. All right, section 3. This is where we get to put on our scientist's hat. The experiment worked, but the results could be better. So how do we improve the separation and get a clearer picture? Yeah, if you look back at that chromatogram, you'll see the yellow and blue spots are kind of bunched up. For a really good analysis, you want those spots spread out. So the question is, how do we make that happen? How do we increase the gap between them? The mark scheme points to 2 correct methods. First, you could just let the experiment run longer, so the solvent travels further up the paper. It's like making a race longer. It gives the runners more time and space to separate from each other. The second method? Use a completely different solvent. Every solvent interacts with the dyes in a unique way, and a different one might just be way better at pulling them apart. You know, I really like this next part because it yanks the experiment out of the school lab and drops it right into the real world of industrial chemistry. It's all about the why. Why do companies do things a certain way? So the question tells us that the manufacturers are super precise. They always use the exact same proportions of yellow and blue dye. Why bother? Why is that consistency so important when you're making and selling a product? Well, the most direct answer is all about consistency, right? The manufacturer has to make sure that the shade of green ink is identical, batch after batch, bottle after bottle. The more technical reason is that the green ink is what we call a formulation. A formulation is a mixture that's been carefully designed with precise amounts of each ingredient to give the final product very specific properties, like its exact color. And here we are, the final part of the question. This one goes right to the core theory. It really tests whether you understand why chromatography works in the first place. This is a pure concept question. Let's break it down. A smaller RF value means the substance didn't move very far up the paper at all. So we're looking for the properties that would make a substance just want to stick to the starting line and not go anywhere. The best way to think about this is like a tug of war. You have the solvent, the mobile phase, trying to pull the dye up the paper. And at the same time, you have the paper itself, the stationary phase, trying to hold on to the dye. So for a dye to have a tiny RF value, it needs to lose that tug of war. That happens when it's less soluble in the solvent, so it doesn't get pulled along, and more attracted to the paper, so it sticks tight. And that right there is the big takeaway for this whole topic.
Everything we've talked about, the calculation, the missing spots, the improvements, it all boils down to this one fundamental principle. Chromatography works because of that delicate balance between how much a substance sticks to the stationary paper versus how well it dissolves in the moving solvent. So, I'll leave you with this final thought to chew on. We've been looking at colorful inks, which are easy to see. But how could chemists use this exact same powerful technique to separate crucial compounds that we can't see, like the individual amino acids that build our proteins? How do they adapt this principle to study the very building blocks of life?